Swayam Prabha. Digital India. Educated India.
Welcome back. So, today I want to take up two things. One is a couple of examples I want to take on power factor improvement, because that is one of the low hanging fruits of this particular application, this particular course that we are doing. As I had mentioned to you earlier, that most of the loads that we come across in our day to day life are having a lagging power factor. So, that means for the amount of suppose S is the MVA which is being drawn, and it is being drawn at a power factor of phi, say lagging. So, then P S cos phi is the amount of watts of work which is being done. But associated with this is also reactive power of S sin phi. The VA I have written in capital volt amperes, and small r in front indicates it is notation for the reactive power. While as I had said earlier, the notation for S is basically just capital VA or kilovolt amperes, megavolt amperes, megawatts, kilowatts. That could be the scaling factor could differ. So, now if this is the lagging power factor, and as I had mentioned, we have discussed already, we are talking still of single phase system here, then S is equal to V into I. So, the current which is drawn is S magnitude of S is magnitude of V into magnitude of I. So, magnitude of S by magnitude of V is the current which is drawn, and if I compensate this, put a capacitor in parallel. So, this is my load, let me put a motor for example here. This is say a single phase motor. Then if I connect, let us say if I put a parallel capacitor here. Okay. So, if I put a parallel capacitor here, this is a supply somewhere, here is my this is somewhere here my supply is there. Now, this load is drawing a active power component and a reactive power component, which is related to this particular motor. So, I am normally this is the current coming from the supply. Normally, this current is going to be equal to this, but I mean is it going to be equal to this value. But now, if I there should be a J here. Now, if I let us say put a capacitor here and it compensates for this is this is lagging power factor. So, it draws a leading power factor current. So, the current is lagging power factor means I should show it with a minus sign here. So, a phasor diagram would look like this. This would be the V, this would be the motor current, this is the phase angle phi, this is the IAM, and this is the IAR. This is negative value sitting here. If I and the capacitor current is going to be IC is equal to j omega c times of V, where V is the supply voltage which is sitting here. Then this V I have taken it as a reference phasor. If you look at it, the current is going to lead it by 90 degrees. So, therefore, this is going to be the IC. So, if I make IC to be exactly equal to the motor magnitude of this IMR, the magnitude of the reactive power of the current, then the net current would turn out to be only this value. So, this value being, that is, the net current will turn out to be only I m cos phi, which is obviously less than I m. So, therefore, suppose this wire had a small resistance, small because it should be so small that my calculations are not significantly impacted, it can be treated as a approximation of correct approximation. Then you can see that this wire resistance now is new wire resistance is so much, while the original wire resistance is I m square r. So, therefore, if you look at the reduction in the loss, taking I m square r common, it is approximately equal to, this is all approximately equal to, because if actually a resistance is put, the currents will alter, but I am assuming like say this is 100 ohms and this is these impedances are somewhere net impedance V by I, which is seen here by the motor, is let us say of the order of 100 ohms, and this is of the order of say 0.1 ohms or 1 ohm. Then this approximation is a valid approximation to do, and we can see that the percentage reduction in loss is approximately, I mean here, since I have completely compensated the reactive power component of the current of the motor, the new power factor is unity. If I do partial compensation, then it will not turn out to be unity, the current would turn out to be somewhere here, for example. So, the reduction in the power factor is reduction in the loss in percentage is going to be equal to this times of 100, which is a significant reduction, could be significant reduction. For example, if the power factor is 0.8, then cos phi is 0.8. So, sin phi will be 0.6. If you square the 0.6, it is going to be 0.36, and 0.36 into 100 would give you 36% reduction in losses. If you actually do the include the resistance and do, the number may come to say 30% or 28%, even then that is also a significant reduction in the losses, and that is a societal benefit. So, therefore, utilities, the distribution companies basically enforce that your power factor should be close to 1 per unit, and if it moves away from a small band of say 0.95 for example to 1, then they will start putting penalty for poor power factor, because you are now responsible for creating a societal loss which is happening in these distribution wires, transmission wires, all the way up it is propagating. So, please compensate your reactive power at the source, and I mean reactive power at the source means the reactive power source is the motor which is generating it, compensate it here and present to utility a power factor which is close to unity. So, that is why this is a very low hanging fruit coming out of our course so far, which is that you can immediately help anyone who is facing a power factor problem with his industry or whatever, how much capacitance or how much reactive power compensation in shunt, this is being put in shunt, that they should deploy to bring unity power factor close to unity. So, let's complete now let's take one concrete example. So, let me just rub this out so that I can use this same space for the work that we are going to do. I think I will rub everything and present to you a clean problem. So, what is given to me now is a load, a motor load. In fact, this discussion is motivated from this problem only, that a 30 kVA single phase motor. So, this is a single phase motor, like your fan is a single phase motor for example, has a power factor of 0.8, all right. A 50, so given to you, what is given to you? P is 30 kVA into cos of phi, which is 0.8. So, therefore, 24 kilowatts. This is the P of the motor. And what is the Q of the motor? 30 into 0.6, if the square root of 1 square minus 0.8 square is 0.36, which, and you take the square root of 0.36, it is 0.6. So, therefore, 18 kVA small r to show that it is reactive, and this is positive, it automatically means that it is lagging, but I am just in addition also writing that it is a lagging. Now, now we have deciphered this statement, a 30 kVA single phase motor has a power factor of 0.8 lag, this has been deciphered. A 15 kVA capacitor is connected for power factor correction. So, this capacitor that is connected, it is connected across this source, for example, 230 volt source. Since it is connected in shunt, this capacitor is connected in shunt and the voltage impressed is going to remain the same. So, therefore, what is going to happen is that it will always draw a fixed amount of kVA, and that capacitive compensation kVA is given to you to be 15 kVA. So, actually QC is minus because it is capacitive. So, it is going to be minus, and I can, but I am just in addition this, if I put the signs properly, I do not need to write lag or lead, but I am going to still put for your benefit lead, and R should be put to indicate that it is only reactive power and not apparent power, which is also V into amperes, but that is square root of P square plus Q square. Now, what is it that is asked to us? Calculate the input in kVA taken from the supply and power factor when the motor is A on full load and B on half load. So, whatever I have written here, this is for full load, this is for full load, and what is required for us, calculate the input in kVA drawn from the supply and the power factor when the motor is on full load and half load. So, if you look at what is being presented here, then what is being presented here is in terms of power. If I want to write, this does not consume any active power, this only consumes active power. So, whatever is the PM is coming, and this is consuming PM plus JQM, and this is generating QC. So, I am writing it as minus JQC. So, therefore, what is coming here is PM plus J times QM minus QC. So, you get basically sorry. So, you get net as PM plus J times QM minus. If I write it as minus QC, then I should not write this minus, because I am treating QC as positive, QM as QC. Once I have written it as capacitor, then I know that I am going to subtract it, because the other one I have written as lagging. So, if I write, I should not do it twice. So, if I write, which I am going to follow the English way of writing it, if I write it as one as lag and one as lead, then the net is the reactive power component lag has the capacitive component lead will be subtracted from the component QM, which is lagging, and so I will get this as 24 plus J times 18 minus 15, or 24 plus J times of 3. This I will write only capital volt amperes. So, this net value S drawn from the supply would be 24 square plus 3 square, I am sorry, this will be, everything is in kilovolt ampere. So, K in small, volt amperes in capital, and I will get the value to be, let me I have calculated it here, 24.06 kVA. So, I will get this as 24.06 kVA. Now, let us draw the power factor triangle. So, this is P, this is Q, even bigger is required, but it is okay, just to give you an idea. P is much bigger than the Q in our case. So, Q is finally the Q is only, Q net is only 3, the P is 24, and this is 24.06 in this triangle. This is the phi seen at the supply. So, cos of phi will be base divided by hypotenuse, which is 24 divided by 24.06, and that number is going to turn out to be 0.9975, 0.9975, and I should write lag with power factor, because cos phi is whether phi is positive or negative, minus 5 degrees or plus 5 degrees, cos phi is the same. So, I have to always append this descriptor that it is 0.9975 lag. So, this is the first part of the question. Calculate the current in kVA taken from the supply and power factor when the motor is on full load. Now, let us do when the motor is on half load. Then afterwards we will finally come to this, what is draw the phasor diagram for each case. So, now let me do the half load stuff here on the right hand side. Let me draw a separator here. So, how much will be Pm at half load? So, the way present it is written, it appears that 15 will become the kVA of the at half load, 30 is the kVA at full load. So, half load kVA will be 15, and I think it is appropriate to assume that the power factor is going to remain the same, because nothing has been said about how the power factor changes. It in real life will actually change, but in this case since nothing has been said about the power factor, we will assume that when we say half load, the kVA has gone by half. So, it has become 15 times of 0.8, which will be exactly. So, it is same as taking half of this value. So, therefore, half of 24. So, therefore, it will turn out to be 12 kilowatt, and Qm will also become half. So, it will become 9 kVAr lagging, and since the capacitance which is used for compensation is a fixed capacitor, it is not being changed, and since the supply voltage is also fixed. So, therefore, the 15 kVAr lead will be the compensation, capacitance compensation with shunt compensation, which is coming from the capacitor here. So, therefore, when you do the sum total of all this, you are going to get Pm plus j Qm minus Qc is going to be equal to 12 plus j 9 minus 15. So, 12 plus j, I am sorry, 12 minus j times of 6, again volt amperes, sorry, kilovolt amperes. So, the S drawn, see it is not compensating at unity power factor is the ideal case, but there is a compromise. If you keep changing the capacitance, then it means you need a variable capacitance, which is extra effort in terms of controls and sizing of the modules of capacitor and all that, while the method which has been used here is a method of one common fixed capacitor, but the motor load will keep changing. So, at some point it will be ideal, other points there will be some deviation from non ideality, because this component we are not able to bring to 0, but even then their loss reduction is going to be there if you have appropriately placed the fix the capacitor value. So, this number S is going to be 12 square plus minus of 6 square is going to be 13.416. Better to write it, even though 6 square and minus 6 square is one and the same, since the Q is actually 12 plus j minus 6, I would prefer to write it as minus 6 of square. And now the power factor cos phi, which is again P by S, that is the P Q and S. This is the way we write show the power factor. Now, what is happening in our case is that the net current Q has become a bit negative. So, it has come somewhere here, and the new, so this is P, this is P motor, this is Q motor, this is Q net after the capacitance a bit over compensation has happened. And so, this if this is the lagging power factor story, now since the Q net has become negative, we are talking of a leading power factor story. In any case, it is this is the S net, and the new power factor is going to be P m the base divided by the hypotenuse, which is the S net, which is going to be equal to 12 by 13.416, which is the value is going to be I am sorry, this 12 divided by I have not looks like I have not calculated it here. This is incorrect value. This should be 12. So let's just do this calculation. Okay, 12 divided by 13.416. 12 divided by 13.416 is 0.8944. So, it is 0.8944 and lead, because the net value of Q is negative. So, therefore, this will be lead. Now, let us do the last part of it, which is draw the phasor diagram for each case. This is quite straightforward, drawing the phasor diagram for each case. So, let me draw the phasor diagram. Here you should draw it to scale, I am just indicating it here, but this is my V, this is my original value of the current, which is okay. I think in this this is just, we cannot draw, we can only sketch in this particular case, because the supply voltage is not given to us. If you take that as 230 volts, then I think everything is straightforward, but I will just indicate to you, and this is the capacitance value. So, that should be shown here, and this is the I net value. So, and in the second case, what is going to happen is, the original current itself reduces by half. So, when you put that I net, it goes here, because the IC does not go under change, this becomes half of the original value, and so the I net in this particular case becomes the leading because of the because of the overcompensation which is happening. See, this triangle has reduced by half, but this current compensation has remained the same. So, therefore, the power factor has become leading. So, assume this to be 230 volts, and I leave it to you to calculate the value of the current before and after, and therefore, all the phasor angles have been calculated, phase angles have been calculated to complete the remaining part of this, which is to sketch the or draw the or to draw the phasor diagram. Now, let us take one more problem, second problem. The load taken from an AC supply consists of a heating load of 20 kilowatts, a motor load of 50 kVA at 0.8 power factor lagging, and a load of 10 kilowatt at 0.6 power factor lagging, because both the loads are lagging, because as we have discussed earlier, the loads typically are only lagging in nature as we come across. A heating load is like a geyser, for example, or an incandescent bulb, that is another one, or a induction heating is third one. So, usually that is taken to be unity power factor, and motors always have lot of windings and iron inside of it. So, they create lagging load. So, calculate the total load from the supply in kilowatts and kVA of the calculate the total load from the supply in kilowatts and kVA also, and the net power factor. So, and what is the B part? What would be the kVAR rating of a capacitor to bring the power factor to unity, and how would capacitor be connected? That should be connected in shunt. We have already discussed this that we do not do series compensation. Series compensation is a different thing altogether. This is it is usually done when you want to alter the impedance of a net impedance of a transmission line or a distribution line. That is not what we are trying to do. We connect capacitor in shunt. So, almost it sees the same constant voltage. So, it gives you a constant kVAR compensation. The load taken from an AC supply consists of a heating load of 20 kilowatts, a motor load of 50 kVAR at 0.8 power factor lagging. Usually motors have lot of inductive element, iron and so on. So, they create a lagging power factor load. A geyser, for example, is just a pure resistive dissipative element. So, therefore, the load is unity power factor, and a load of 10 kilowatt at 0.6 power factor, again lagging. So, what is asked now from us? Calculate the total power from supply in kilowatt and kVA and the net power factor. That is one thing which is asked. Then what would be the kVAR rating of the capacitor to bring the power factor to unity, and how would the capacitor be connected? So, it should be connected always in shunt. If the supply is single phase 230 volts 50 hertz AC, calculate the value of the capacitor. So, let us do it. Let us take the A part. There is a heating element. So, I will write its load as P plus JQ1 as 20 plus J0. The unit I am writing here as kVA, because I am writing for P plus JQ. Now, motor load of 50 kVA at point. So, this I am going to write it as P plus JQ2. So, P is going to be how much? Power factor is 0.8, S is how much? 50. So, 50 into 0.8, 40 kilowatts is the load active power, and if 0.8 is the cos phi, then sin phi is 0.6. So, S sin phi will be 50 times 0.6, which is the reactive power, which because it is lagging should be written as plus J, and so 50 into 0.6 will become 30. So, 50 into 0.6 will become 30, and a load of 10 kilowatt at 0.6 power factor. Now, this is slightly different calculation here. P3 is given to you as 10 kilowatts directly. So, you do not have to do anything for that. S has to be calculated. It is 10 divided by 0.6 kVA. Why? Because P is equal to S cos phi. Cos phi is given as 0.6, P is given as 10. So, S becomes 10 divided by 0.6, and so Q, which is equal to S sin phi, will become 10 divided by 0.6 into sin, if cos phi is 0.6, then the sin phi will be 0.8, and so therefore 10 divided by point this thing, which is 40 by 3, or 40 by 3 is going to be 13.33 kVA. So, now we have got now what we have to calculate, and this is also I do not have to write it lagging, the plus indicates lagging as well as lagging nature of it. So, calculate the total load. So, just sum it here. So, you will get 50 plus 20 70 plus j times 43.43 kVA. So, calculate the total load from supply in kilowatt and kVA. So, kilowatt is obviously 70, and the other kVA asked is the S value, the apparent power value, which is 70 square plus 43.33 square, which is going to be equal to 70 square plus 43.33 square. So, this value comes out to be 82.32. So, this value comes out to be 82.32 kilovolt amperes, and the net power and the net power factor. So, the net power factor is going to be cos phi is the P net, which is 70, divided by S net, which is 82.32, and this number is going to be equal to 0.85026 lagging. 0.85026 lagging. Now, let us come to the B part. What should be the kVAR rating of the capacitor to bring the power factor to unity? So, it should completely cancel this reactive power component 43.33 kVAR, and so QC should be, rating should be 43.33 kVAR. This is the, to correct power factor to correct the power factor to unity. What would be the kVA rating of the capacitor to bring the power factor to unity, and how would the capacitor be connected? Shunt, of course, and if the single phase 230 volt 50 hertz, if the supply voltage is single phase 230 volt and 50 hertz AC, calculate the value of the capacitor. So, this QC value is nothing but equal to omega C V square, is it not? Because this is in shunt. So, this capacitor is in shunt, its impedance is 1 by j omega C, the voltage, supply voltage V is impressed here. So, the current is equal to I j omega C V, and so if you do V I star, it is minus j omega C V square. This minus only indicates that it is capacitive in nature. So, but only thing that I am interested in is actually the magnitude of it, which is j omega C V square. So, therefore, QC can be written as omega C V square, and so the C will turn out to be QC divided by omega V square. So, this will be 43.33 divided by 2 pi 50 into 230 square, and I have calculated this value. This value is going to be equal to, yeah, so one more small correction. This is being in kVA, I should kVAR, I should write this in into 10 to the power 3 to calculate the values in farad, and that value is turning out to be so many farads, which is equal to, if you multiply by 3, then it is 2.670 millifarad. So, this is the value of the capacitance which I need to bring the unity power factor, to bring compensate and bring the power factor to unity. Here there were 3 loads, 3 composite loads were there, like in your house, for example, you know, the geyser is there in the bathroom and refrigerator is there, for example, let us say in the or a fan or a refrigerator is there in the kitchen, and then somewhere else another load is there. So, all these loads sum together and come on your supply, the utility behind the meter which is put, you know, that meter from that. So, this is your supply coming from this is your meter, and then this is room, this is supply for room 1, this is supply for room 2, let us say this is supply for room 3, and each of these 3 loads are coming here, and they are taking P plus JQ1, P plus P2 plus JQ2, P3 plus JQ3, and then the summation comes across your meter. So, the meter records consumption for the summation of all of it, and then again the capacitor for unity power factor should be placed again in the shunt here, so that the meter records the value of Q after compensation. So, this is the P plus JQ coming from the net P plus JQ of your load, and this is the capacitance, and then that subtracts from here, and then that net value of P plus JQ net is what comes to the meter. So, it sees a smaller value and a better unity power factor, which is what is told to the utility, and then the utility is happy. It says, okay, I know you are drawing a lower value of the current because your power factor is close to unity. So, that is an important point that we have to realize. Now, we have some time. So, let us start discussion of 3-phased balanced system. I have already discussed with you why it is very important to have 3-phased balanced system. Now, what I am going to discuss with you is that there are 2 possible connections. I am taking for a supply for the sake of discussion. The same thing applies on the loads, 3-phase load side also. I can have a 3-phase supply which is connected in, for example, a star configuration. This is shown, the angles are not physically there in the apparatus, but are just shown on the diagram to indicate the 120 degree phase shift of the supply. So, this is called, this is your A phase supply, A phase balanced supply. It does not look very good, but it is okay. This is a phase supply which is connected in star configuration. Now, if these 3 terminals are available at the box outside of your generator box. So, whole of this thing is sort of generator is there in a box and this ABC A, B and C terminals are available here. So, if you draw the phasor diagram, if I say this is my VA, this is VB, this is VC, and let this be connected to a 3-phase load, could be an induction motor, could be anything, could be impedances connected in star or could be some impedances connected in delta, but it is a balanced 3-phase load. So, then if this current is IA, this is IB and this is IC, then this current which is flowing in these lines outside from my supply to the load, I will call them as line current, and these are called the line terminals, and the voltage which is developed across it, I will call it as line voltage. So, in this case you can see that line current is equal to phase current. I am just showing it for A phase, but the current which is flowing in the line is exactly the current which is going to flow through the phase, and the line voltage. So, there are 3 line voltages, 3 line currents for 3, because it is a 3-phase system, 3-phase line 1, 2 and 3, but magnitude wise all of them are carrying the same line current IL, because phase angle wise they are 120 degree apart. And line voltages, if you look at it, you have 3 line voltages. I will connect this one. So, draw the arrows as follows. So, VB, this is my ground or neutral. So, VB plus VAB, the line voltage, will give me the voltage of the A phase VA. So, in other words, VAB is VA minus VB, VBC will be VB minus VC, and if one is putting arrows as well, one can put it everywhere across, and VCA will be VC minus VA. If you do that, basically if you, as I showed you here, see the load which is, suppose you connect some load here, then that load is going to see a voltage of VA minus VB. So, that is called the line voltage. If something gets connected here, it sees a voltage of VB minus VC impressed across it. So, that is another line voltage, and the third one is VC minus VA, which is this particular line voltage. So, VB minus, so VB plus VAB gives you VA. So, when I write VAB, the first is A and the arrow comes correspondingly at the A phase point, this is A, this is B, this is C, and the tail comes at the B point. So, when I write VCA, the arrow comes at VC and the tail comes at VA. When I write VBC, the arrow comes at VB and the tail comes at VC. In this particular case, because this is a vertical line, by the equilateral triangle geometry, this will turn out to be a horizontal line. Now, if you calculate the lengths of this, if you calculate the length of this, and this, these are the three lengths of equilateral triangle. So, they are equal. So, let us do that. VAB is VA minus, remember once I have defined that A is the exponential operator which rotates in the anticlockwise direction by 120 degrees. So, a lag is basically A inverse, which is e to the power minus j 2 pi by 3. So, therefore, VAB is VA minus VB, which is 1 minus A inverse of VA. So, I can take VA common and write this as 1 minus A to the power minus 1 of VA. So, now let us do it geometrically. This is 1, this is A inverse or A square, this angle is 120 degree. So, I take minus of A inverse. So, I come somewhere here, this is minus of A inverse, these lengths are equal, and so this is 120 degree. So, this becomes 60 degree. So, now I complete the parallelogram. And I calculate this length, and I calculate this length, and I look at this particular angle. So, if you connect this line, this angle is only 30 degrees. So, therefore, 1 will be projected by cos 30 degrees. So, therefore, this length is going to be just root 3 by 2, and by symmetry this is also root 3 by 2. So, therefore, the whole of this length is going to be equal to 2 into root 3 by 2 or equal to root 3. So, if this is 1, this is a length of root 3 and it leads this unity phasor, the vertical unity phasor, the reference phasor by half of 60 degrees. So, therefore, by 30 degrees. So, therefore, this is going to be equal to VA root 3 e to the power j pi by 6. So, VAB is VA root 3 e to the power j pi by 6, and I will let you complete the remaining part of this. So, the modulus of VA is going to be how much? Root 3 times of modulus of VA, or in other words the line voltage or line to line or line voltage is root 3 times the VA to ground or VA to neutral is called the phase voltage. So, if you now look at and the line voltage in a star connection, this is called a star connection, a line voltage in the star connection like this, line voltage is leading the phase corresponding phase voltage by 30 degrees. So, it is leading by 30 degrees, and so now if you look at the P3 phase, it is going to be 3 times V phase I phi star, or if I directly write it as S3 phase complex as 3 Vp Ip star, then the P3 phase will be 3 times of Vp Ip cos of phi, and Q3 phase will be equal to 3 times of Vp Ip sin of phi, but root 3 Vp I can write it as VL, and in a star connection the phase current and the line current are the same. So, therefore, I can instead of Ip I can write it as IL, and so the 3 phase power is VL IL cos phi for the star connection. This is unit is watts 3 phase, but the unit is watts, and Q will be 3 VL IL sin of phi. Now, in the next class I will discuss another balanced connection which is commonly used, which called as a delta connection, and show that in terms of the phase voltage 3 phase powers for 3 phase active and reactive power, the formula is always 3 VL IL cos phi and root 3 VL IL cos phi and root 3 VL IL sin phi, whether it is a star connected load or whether it is a delta connected load. We will now break here for today. Thank you.